Thanks a lot, Joanna. Thanks a lot for the kind introduction. I hope you can all hear me well and you can all see the screen. So as Joanna already introduced, so today we are gonna be taking a deep dive into two well-established techniques for signals, for analysis of periodic signals, lock-in amplification and boxcar averaging. So we will delve into their principles, differences, and I hope that at the end of this hour, you'll be able to take conscious decisions when it comes to deciding which approach to pursue for your own measurement. So I would like to start by motivating why it is essential to choose the right measurement approach. Well, in a way, the reason is quite obvious. Proper signal analysis is key to achieving high measurement precision, preserve information content, and reduce measurement times. For example, taking this to the limit, we can imagine the impact of an incorrect or a correct signal analysis approach when it comes to measuring very small effects at the boundary, for example, of length scales, as it was for this here image on the left in the LIGO experiments, where they needed to detect length changes in the order of 10 to the minus 21 meters. Or, for example, also when we are trying to detect effects at the boundaries of timescales, as, for example, here in this right-hand side figure, where one of the first attosecond pulses measured with resolutions down to 10 to the minus 17 seconds. Notably, this picture on the right comes from the lab of Ferenc Krausz, one of the physicists that was awarded the Nobel Prize recently. So, in the end, the challenge is always the same. Once the signal is measured, it's key to preserve the information content to make sure that the signal has the quality that we need. And this is where we, Zurich Instruments, come into the game. So, our mission is to provide best-in-class dynamic signal instrumentation for advanced research and development labs. And how do we do that? So our approach is to take off-the-shelf hardware with adequate characteristics and adequate speed, sensitivity, noise, and general specifications, and combine this with a software infrastructure that allows the hardware to perform at its best, but also gives the user efficient workflows, compelling APIs, intuitive user interfaces. And with this approach, we're also able to add new features to the instrument over time, thereby increasing its value. Here at Zurich Instruments, we have 4 instrument pillars, namely the quantum control systems, lock-in amplifiers, boxcar averagers, and impedance analyzers. Today, as the title suggests, we're going to be looking into lock-in amplifiers and boxcar averagers. And who is making all of this possible? So here, we at Zurich Instruments, this company was founded in 2008 as a spin-off of the ETH in Zurich. It counts nowadays more than 150 people from 20 plus nations. So the headquarters are in Zurich, Switzerland, where I'm also sitting at the moment. But we have sales offices scattered throughout the world: USA, China, Germany, Korea, France, and Japan. And since the 1st of July 2021, we are part of Rode und Schwarz. So what kind of answers can you expect what kind of questions can you expect to be answered today? So we will start by understanding why, for example, lock-in amplification is a beneficial measurement technique on a broader level. Then we will also, of course, delve into the boxcar averaging, compare it to the lock-in amplifiers, and try to understand when one measurement approach is better or comparable to the other. And we will also look at some instrumental parameters that affect the end measurement results. All of this will be supported by some application examples. For example, for linear spectroscopy, tunable diode absorption spectroscopy, and with pump probe-based spectroscopies. At the end, we'll also have a live demo showcasing what digital instruments are capable of, what our lock-in amplifiers, especially this guy here, are able to do with a digital signal processing technique. So nowadays, so today, the focus will be mostly in optics and photonics applications, but boxcar averagers and lock-in amplifiers serve a large variety of applications. From scanning probe imaging, from material science, electrical pump probe, failure analysis. Generally, when the aim is to measure very small signals buried into the noise, lock-in amplifiers or boxcar averagers can be very beneficial to extract good quality signals. And so first, what is the information that is present in signals? Well, there could be different types of parameters that one needs to measure. For example, we can have a parameter variation that leads to an amplitude change for a certain time duration, or maybe we need to measure a sinusoidal modulation that we need to compare to a certain reference and measure its amplitude and its phase, or we can have a pulse train where we need to measure the intensity or other characteristics of this type of waveforms. Importantly, we need now a way to define the quality of a measurement. So the most common parameter used for this purpose is the signal-to-noise ratio. A unitless quantity defined as the ratio between the signal in terms of its average and the noise in terms of its standard deviation. Now, this is generally called the linear signal to noise. There is also a version expressed in decibels. Okay, so basically taking the linear signal to noise ratio and with a log base 10 and 20 times log base 10 the linear signal to noise ratio. Now, what the signal-to-noise ratio is can be qualitatively understood by looking at how spread out the results of a measurement are around its average value. Now, we can see here two different curves, orange and blue, and we can clearly see that for the case of the orange curve, the results of the measurement, each data point is not that much spread out with respect to the average of the signal. While for the blue curve, this effect is much more visible. And indeed, for this exemplary case, we have that the signal-to-noise ratio of the blue curve is worse than the one of the orange curve. Just to give you an idea of understanding order of magnitudes here, so 10 decibels is generally more or less a factor of 3 in terms of amplitude of the signal for the linear signal-to-noise ratio. Now, but before analyzing any signal, we need to first understand and characterize the noise in our experiment. So here, on the right-hand side, we have a typical noise frequency spectrum that is characterized by different components. So we can start by looking, for example, at this dark gray area here that is indicated, that is generally referred to as the 1 over F or pink noise. And its characteristic is that it increases as the inverse of frequency by approaching DC. Then we have this light blue background that is generally referred to as the white noise, or the white noise. Then there are also some noise spikes, coherent pickups. For example, the common ones of the 50-60 Hertz power line where we plug our instruments. Now, if we are taking a photonics experiment as an example, typical contribution, for example, for the 1 over S noise or 1 over F noise might come from our laser source. So the relative intensity noise of our laser source has a typical profile like this. Whereas for the white noise, generally the contributor is also the detector, so the shot noise of our photodiode of our detector. Now, generally, the approach to reducing noise is averaging. Now, averaging is equivalent to low-pass filtering. And if we are doing averaging, we are basically doing low-pass filtering around DC. And this means that we are basically filtering our signal where the noise is the highest. So, in order to shift the band of interest to a region with lower noise, we need to introduce a modulation in our signal. So, for example, typical examples in optical experiment of modulation can be chopper, amplitude acoustic modulators, or electro-optic modulators. Once we have modulated our signal, we also, of course, need to demodulate the signal at the very same frequency, for example, with the help of lock-in amplifiers and boxcar averagers. Now, to give you an idea of the effect, here I have plotted the step response with different modulation frequencies, starting with the blue at DC, and you can clearly see that as this modulation frequency is pushed towards higher values, the step response, the signal to noise, visually of the spectrum of the step response becomes better and better. Now we have introduced the modulation in our experiment. We need to choose the correct instrument to demodulate our signal. Now here it would be easy for me to say, yeah, Zurich Instruments lock-in amplifier are the best, but this is not the point. So of course the choice of a certain instrument can depend on many things. There are several ingredients that go into the choice of a certain instrument. Of course, next to the input bandwidth that is basically defined by the modulation frequency in our experiments, there could be, for example, also parameters like the measurement bandwidth, so how fast I'm able to measure, or the input noise of the instrument, or maybe the dynamic reserve. Furthermore, in modern digital instruments, there is much more than simply, for example, a lock-in amplifier or a boxcar averager. So there is integrated tool set for time and frequency domain analysis, as for example, scope, sweepers, or multiple modulators that allow you to demodulate your signals at multiple frequencies. This is here the fleet of our instruments that are now available, and we have that basically they can cover all the range from DC, from 0 Hz up to 8.5 gigahertz, so up to the microwaves. With the last two additions to our portfolio, the GHFLI and the SHFLI lock-in amplifiers. So now we have already introduced the concept of, or the name of lock-in amplifier. So let's now try to understand how the lock-in amplifier works and how it can makes a measurement. So the idea is pretty simple. So we take our signal of interest, in this case here, that's buried into the noise, and we multiply it with a reference signal at a certain frequency, in this case, F mode. This multiplication then is basically as the effect of shifting our signal to F mode, around the F mode, the modulation frequency. Then the result of this multiplication is sent through a low-pass filter that filters out all the spurious component that we don't want. And after the low-pass filter, basically we are able to recover both amplitude and phase of our signal with respect, the phase with respect to the reference that we multiply the signal. For lock-in amplifiers, generally low-pass filters are simple RC filters, so that are depending on the filter order, as we will see in a second. There are different multiple filters cascaded one after the other. Of course, now the overall transfer function of a lock-in amplifier can be thought as basically the one of a band-pass filter with arbitrarily set center frequency, and we will see in a second also bandwidth. Now, an important note is that modern lock-in amplifiers are digital instruments, okay? So performing everything in the digital domain with digital signal processing techniques. This means that these low-pass filters here, the filters here, are not actual RC filters with resistance and capacitance, but these are modeled, okay? These are digital models of RC filters with which our multiplied signals, also here in the digital way, is multiplied to obtain amplitude and phase of the signal. So the most important element that affects the quality and in turn the SNR of our measured signal is the low-pass filter. Now, and of course its setting. So the most important setting is the measurement, the low-pass filter bandwidth. The filter bandwidth basically defines the measurement bandwidth. That is how many frequency components are allowed to go through the filter. So if we now have a look at the filter functions for different filter bandwidth here on the right hand side in the frequency domain, we can see that basically higher filter bandwidth means that the cutoff frequency of my filter is at a higher frequency. As it's clear, higher bandwidth filters allow more frequency components to go through the filter, meaning that also more noise can leak through to the filter itself. Now, at the same time, we can also see that large filter bandwidth have the advantage of, if we go back to the time domain, of settling faster to the new value. So if something changes in my experiment, higher filters with higher bandwidth are basically settling faster than filter with lower bandwidth. So in general, the rule of thumb is that the measurement bandwidth, so the low-pass filter bandwidth, should be as narrow as possible to filter out as much noise as possible, but at the same time also support all signal components. What this means can be seen better in this example here. So here I have a signal with 3 different low-pass filter settings, and we can start by with the left-hand side. We can see that the signal is visible, however, there is quite a thick noise background that you clearly see overlaying with the signal. If we now, this is with a quite high filter bandwidth. If we now go to the right-hand side, we can see that now with a much smaller filter bandwidth, we are able to kill this noise, to reduce this noise, but at the same time also smearing out our pulses, meaning that we are also filtering part of the frequency components that make up our signal. And here in the middle, we can have the best compromise for this specific case, where both the noise is reduced and the peaks are clearly visible and well resolved. The next parameter that one can play around with is the filter order. So filter order meaning, this simply means that there is a number of filters that are cascaded one after the other. As we can see here in the frequency domain plot for different filter orders, low-pass filters, we can see that as we increase the order of the filter, we basically increase the roll-off curve, the steepness of the roll-off of the filter. At the same time, however, similarly to the measurement bandwidth, as we increase the filter order, also the step response gets delayed. Basically, when do we need a higher filter order in this case, you might wonder? Well, this is generally used when we have some frequency component of the noise that is very close to the ones of our signal. It can be clearly seen here in this example, where we have a signal demodulated with the filter order of 1, and we can clearly see that there is some ringing on top of this signal, meaning that there is some interference between some frequency components of the noise and frequency components of the signal. Now, by increasing the filter order up to 6, we can clearly see that this ringing is suppressed. So again here, rule of thumb, with the filter order should be kept as low as possible to basically make sure that the signal will settle as fast as possible, but also high enough so that all the frequency component, the spurious frequency component, are suppressed. Now I would like to show you one example of spectroscopy when we use lock-in amplifiers for very common experiments. So the experiment is tunable diode laser spectroscopy, and as the name already implies, this is basically an experiment that uses some diode lasers whose wavelength can be swept, can be changed to analyze some sample. So in this case, generally what is typically done is a technique used to find out and to explore properties of gases. So basically the setup is quite simple. We have our laser that is outputting a certain wavelength, then is going through this gas cell. So in the gas cell there is our gas pieces that we want to investigate, and as the wavelength of the laser is swept, depending on the species that the gas inside the gas cell that there is inside the gas cell, at some frequencies this gas cell will start to absorb some light, thereby having a reduction of intensity when hitting the photodetector. Now, many times what one wants to do is to measure ultra low, for example, concentration of the gas, and the signal being proportional to the concentration of the species that I wanna see. As we go to ultra low concentrations, also the signal becomes extremely small to resolve. A way that is generally done to improve the sensitivity is to include, together with the sawtooth signal that is going to the laser to change the wavelength, also a tiny sinusoidal modulation on top of the sawtooth signal. This basically modulates both the amplitude and the wavelength, and basically, as we've seen before, shifts the signal of interest to the frequency of the modulation. Here, also, of course, after the signal is then picked up by photodetector, we need a lock-in amplifier that demodulates the signal at the same frequency. And here you can see an example where basically all the setup was provided by our lock-in amplifier, both the exciting signal to the laser and also the analysis of the signal with the lock-in amplification. Okay, I would like to shift the focus and have a look at a type of signal as the one here in the picture. So the information in this periodic signal is concentrated only in a short amount of time, as you can see here. When compared to its period. So this type of signal is generally referred as low duty cycle signal. The duty cycle of a signal is basically a measurement of how much within the period the signal is high, and it can be defined as the pulse width of our signal times the repetition rate, or the inverse of the period, times 100 to have it in percentage. For example, if we have a pulse width of 10 nanoseconds, which can be typical from photodetectors in a photonics experiment, with a repetition rate of 100 kilohertz, we end up with a duty cycle of about 0.1%. So I think also intuitively, it makes sense to only measure the signal where it's high and not where there is, when it's low, disregarding everything else where the noise is present. Now, how can we do that? Well, here is where the Boxcar Averager comes into play. Let's now understand its working principle. Now, as we're going to see, it's some similarities also with lock-in amplification. So, instead of for the lock-in, we multiplied our signal with the sinusoidal reference waveform. For the case of Boxcar averaging, what we are doing, we are basically multiplying our signal with a square wave with arbitrary duty cycle. The result of this multiplication is the sent to integrator, where that basically integrates everything within our high time of the Boxcar function of our square wave. Then, as for the lock-in, this is sent through a low-pass filter, and then with this we can recover the signal amplitude. Now, unlike the lock-in, where the low-pass filtering was done with, say, RC filters, here the low-pass filter is simply a moving average filter. So basically, how many of the boxes are averaged before the result of the measurement is sent out. Now, in order to understand better when this kind of technique, when Boxcar averaging and lock-in, and how they compare, and how can one be maybe sometimes a better choice than the other, let's go back to our pulsed signal. Now, if we now take the Fourier transform of such a signal, what we will see is that basically the information in the frequency domain is spread out across many harmonics. Okay? So if we now were to take a lock-in measurement, what we would essentially do, we would basically perform the information, capture the information only at the first harmonic of the signal, basically losing all the information in the higher harmonics. If we now instead start to box our signal with our Boxcar averagers windows, what we can see is that we can increase the bandwidth of our detection by making the Boxcar window smaller and smaller. This, as you can see here on the right, basically the detection bandwidth of our Boxcar averager is basically extends as 1 over is inversely proportional to the width in time domain of the Boxcar window. So this is how basically the Boxcar averager works, and why in certain situations this is it makes sense to use such a tool when the information of our signal is spread across multiple harmonics in the frequency domain. Now, many times in Boxcar averagers there is also this additional option that is called baseline subtraction, where basically a second window is placed somewhere within the period of the signal where no signal is present, and then it's integrated as the one around our signal, and then the output of my measurement is going to be the difference between the baseline, the Boxcar window with my signal and the baseline, so the subtracted baseline. This basically has the effect of suppressing DC and slowly varying components. And if we look at the frequency domain now, it's basically just taking the odd harmonics of my signal. In some experimental instances, maybe it's also interesting to directly perform the difference between two consecutive pulses, as maybe the information in my experiment is it's inside the difference between two consecutive pulses. This is, for example, the case, as we will see maybe in a second, for pump probe spectroscopy, when sometimes the one pulse is used as a reference and one pulse carry the information that we want to look at. Now, for the lock-in, as we've seen that basically the signal settling is nonlinear, is exponential due to the characteristics of the low-pass filter, and it depends basically on both the filter bandwidth and the filter order. For the case, instead of a boxcar averager, we have that the settling only depends on the number of averaged boxcar windows. And since it's just a moving average filter, its settling is completely linear. So, and this means that there is basically no correlation with prior data points. Typical, let's say, applications of boxcar averager, or typical application where boxcar averagers, but also lock-in amplifier, depending on experimental configuration, are used, are pump probe-based spectroscopy. Now, there is countless variation of this type of technique, but the basic principle is essentially the same. So what we have is that, in a nutshell, we have two co-propagating pulses coming from the same laser, from the same source, where one pulse is the pump, and in shining onto the sample, it basically induces some sort of photochemical processes that are then probed, explored by the second delayed pulse, the probe pulse. The pump pulse is modulated at some frequency, so that basically what is measured is basically the relative absorption of the probe when the pump is present and when the pump is not present. By varying then the delay line between the two, the delay between the two pulses with the delay line, one can fully recover the dynamic signal of the photo-induced chemical processes. As we've seen, the pump pulses modulation, and depending on the type of modulation that the pump has, either lock-in amplifiers or boxcar averagers can turn out to be a very useful tool to resolve signals that are usually very, 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 very small for this type of experiments. Now, as I mentioned, there's so many variations of this technique where different combination of pulses can be used to explore different processes. So, for example, we can have this visible pump or near probe, or we can also have that one of the pulses, the pump of the probe, is replaced by a terahertz pulse, for example, in the case of terahertz time domain spectroscopy. But also we have imaging applications where pump probe is used to acquire images in microscopy. Many times, given the high pulse intensity required to generate nonlinear processes to have these pump probe measurements, high power, low repetition rates laser are used, making the duty cycle of the signal very low, and thereby making also boxcar averagers a very attractive measurement technique for this type of signals. And it's why here I want to show this very, very nice example where this group has performed some stimulated gamma scattering microscopy on some samples, and then directly basically compared the lock-in amplifiers and the boxcar averager, giving some quantitative results in terms of measurement time. So the setup also here is quite straightforward. We have they have a 40 MHz laser that was split into two branches. One branch, the pump branch, that was modulated half the frequency of the laser, so 20 MHz. So one pulse on, one pulse off, and then the probe and the pump, when they're recombined, shown onto the sample that was of course moved, scanned, and basically what was recorded was the dwell time, the pixel dwell time for each pixel. Now, what they found out is that for this configuration, to achieve a certain signal-to-noise ratio, the Boxcar averager would take half of the time for each pixel, so the dwell time of the pixel would be half than the case for the lock-in amplifiers. And this is good, of course. This is because it reduces measurement time, but also comes to the avoiding photo damage of investigating samples, meaning that we have delicate biological samples. This we need to shine light to have good signal-to-noise ratio half of the time than with, for example, lock-in amplifiers. Now, I know that many of you may be now asking themselves, okay, but this is all nice, but then how can I tell which measurement approach leads to the best SNR for my experiment? Is there a recipe for this? So, well, I mean, for limit cases, we can say that if we have a signal that is basically purely sinusoidal, for sure, I would like to measure my signal with the lock-in amplifier. At the same time, if I have a signal whose the duty cycle is ultra low, for sure the Boxcar averager will be the best choice. However, for more complex signals, what is generally the case, this is no straightforward answer to this question. And this is because while the duty cycle is of course an important factor to consider, there might be also other things to consider when it comes to, for example, the frequency of the actual frequency of the signal, some specific noise sources, synchronous interference that are exactly the same frequency of my signal, maybe also the measured harmonics that the instrument can provide. So basically the interplay among all these factors can be very not trivial. Therefore, generally the best strategy for signals that are complex is to try out both approaches and then evaluate which leads to the best SNR. Then you might ask yourself, okay, but now do I need to basically have two instruments to then decide which one to use? Well, it turns out that with our instruments, with our lock-in amplifiers, you can have both instruments in the same device, so you don't need to choose. You can compare your signals, the signal-to-noise of your signal, and then decide which is the best measurement approach for your experiment. That is why now I'm gonna show you a demo with one of our instruments, the UHFLI lock-in amplifier, and measure a signal that I actually produce with this very same instrument. And basically I output the signal and measure it with a signal input with both techniques, lock-in amplifiers and Boxcar averagers. And we can see how changing certain parameters on the measurements, these affect the signal-to-noise ratio of the measurement. So now I'm gonna move to the software. I hope you can all see the software. Now what I'm doing, as I said before, I'm creating some Gaussian samples, Gaussian pulses at a certain repetition rate. In this case, 2.1 megahertz. To understand how they look like, we can also have a scope on our instruments where you can basically run the scope, and you can see now that if I zoom in, I have a train of pulses at a certain repetition rate with a certain period. We can also check the period, so the distance in time between these pulses, and we can see that basically the difference is exactly 1 over the repetition rate of this frequency here. Now, what we can do, we can perform a measure with both Boxcar and a lock-in. So let's now start with the Boxcar. Okay, so the Boxcar units on our instruments, what they have is the so-called periodic waveform analyzer, PWA. So if I now run the PWA, what I see here only just one single pulse. And this is because what I've done, I locked the PWA to the frequency of the repetition rate of my pulses. And the PWA basically plots the one single cycle of my pulse train. And this is why also, for example, here the x-axis, as you can see, is in phase, because this is basically from 0 to 360 degrees, so one full cycle of my pulse. Of course, this can also be changed to time domain. And as we've seen before, basically we can also see how many the harmonics component of my signal. So now if I increase this, and if I go to linear, we can see basically that my signal is composed by a certain amount of harmonics. So this is basically the harmonic contribution of my pulsed signal. Now going back to phase and running again, what we can do now, we can then perform our Boxcar averager measurement. So what we're doing, we're going to set the window the Boxcar Averager window around my signal. Okay, so copy from cursors, I activate the Boxcar gate, and we're also gonna set the baseline window. Basically, so somewhere where there is no signal in order to have the subtraction between the Boxcar gate and the Boxcar baseline. Now I'm gonna copy this from cursors. And then the other thing that we can set is of course the averaging periods. If one were to put one here, each of the basically Boxcar gate, integrated gate would be sent out as a measurement instrument, as a measurement result. And this is sometimes known as gated integration. Now, going back to our, we are now doing some averaging here, 256 basically gates before we send out the results. And this basically turns into a certain averaging bandwidth that is essentially defined by both the averaging periods and the repetition rate of my signal. Now, in order to have a comparison between lock-in amplifiers and Boxcar Averager, what we are doing, we are basically doing a lock-in measurement with the same measurement bandwidth, so that we can compare the signal-to-noise ratio apples to apples. If I now do this and I run the scope, you can see that it's something I have to enable. This is enabled. Okay. I don't know why it's not. Okay, now you can see both. So basically what you can see now that in this precise configuration, what we have is that the signal-to-noise ratio of the two measurements is comparable. So they are leading to the same, more or less, signal-to-noise ratio. What is interesting to see is that, for example, here for the lock-in measurement, so the blue line, we are measuring an average of about 3 millivolt for this case, while for the Boxcar Averager we are measuring a higher average value because we are also integrating, we are also basically summing all the contributions from the higher harmonics. Now, what we can do, we can basically, to see how changing for example, the duty cycle of my signal changes the measurement result, what we can do here, we can reduce this drastically to, for example, around 10 kilohertz. As you can see already, basically the width of my pulse with respect to its period, so the width of the pulse itself has not changed, but the width with respect to its period has become much smaller. Now we can zoom in here to increase the resolution. Okay, and now we can see our pulse that actually has the same width, okay, as before, but in this new duty cycle, in this new repetition rate, pulse train takes much less space in time. Again, we can now have a look, for example, at the harmonics once more, and we can see now that now the harmonic contribution of my signal is much larger. So there are many more harmonics that contribute to my signal. Now going back to phase, we can then again run the measurement. Here again. Now we can set the Boxcar window again around my signal. Okay. So this, and then I now set the baseline somewhere where there is no signal. As you can see here, basically the averaging bandwidth, given the fact that the repetition rate has changed a lot, the averaging bandwidth has also changed, going very much lower to about 18 Hertz. So again, now to compare this type of measurements with the lock-in measurement, we also need to change the bandwidth of the lock-in to have it, to compare apples to apples. Now, if we now have a look at the plotter, we can clearly see that for the case of a Boxcar Averager, what we have is that the signal-to-noise ratio is much better. It's much higher, 59 dB against the 23 dB of the lock-in measurement. So almost 40 dB different. This is almost a factor of 100. Okay, so now going back to our presentation and let's wrapping it up. Basically, what we have seen is that lock-in amplifiers are generally versatile instruments that are used to recover signals that are small and buried into the noise, as we've seen also with the example of TD LAS spectroscopy. Boxcar averagers can be advantageous in case where pulse signals, so where the duty cycle of my signal is low. However, it's not always easy to give a clear answer whether one technique is better than the other. So the idea, the best way is to basically try both techniques, both approaches, and then decide based on the results that the SNR basically of my measurement, what is the best technique to use for your specific experiment. With this, I would like to thank you for your attention, and I'll be happy to take some questions.